everyone, and welcome to English 1 at the University of Crete. I'm Noni Rizopoulou, and in this video we'll explore how computers are actually built, how hardware components interact, how instructions flow through a system, and how design choices affect speed, efficiency, and performance. The von Neumann architecture is named after the Hungarian-American mathematician John von Neumann. At its core, it describes a computer design where both data and instructions are stored in the same program. This idea has become the foundation of modern computing. We now call any computer that follows this principle a stored program computer. In this architecture, a machine instruction, also known as machine code, is simply a program that the computer's central processor can execute directly without any further translation. This design allows computers to be flexible. The same hardware can perform different tasks simply by loading different programs into memory. A computer is made up of three main subsystems. The CPU, Central Processing Unit, is the brain of the computer. It processes information, executes instructions, and controls other components. You can think of main memory as the computer's short-term memory. It stores data and instructions that the CPU needs immediately. Input-output devices are the interfaces between the computer and the outside world, like keyboards, screens, and printers. They allow communication with users or other systems. We can draw analogies to living organisms. The CPU is like the brain, directing activity and making decisions. Memory is similar to short-term memory in humans, holding information for immediate use. I/O devices are like our senses and limbs, allowing us to perceive the environment and act upon it. Together, these subsystems enable a computer, like an organism, to process information, respond to stimuli, and interact with the world. The CPU, or Central Processing Unit, is essentially the brain of the computer. It includes the circuitry that manipulates data, executes the instructions of a computer program, and performs operations according to those instructions. The CPU has three main components. Arithmetic logic unit performs arithmetic operations like addition and subtraction, as well as logical operations such as comparisons. Think of it as the part that solves problems and makes decisions. The control unit directs the operations of the CPU and coordinates the activities of all other components. It acts like a manager, ensuring tasks happen in the correct sequence. Registers are small, fast storage locations inside the CPU that hold data temporarily during processing. You can think of them as the CPU's short-term memory, holding information that is actively being used. Together, these components allow the CPU to process data, execute instructions, and control the overall operation of the computer. Main memory, also called primary storage, is the storage directly accessible by the CPU. The CPU continuously reads instructions from main memory to execute programs. Main memory consists of electronic circuits embedded on a small flat piece of semiconductor material, commonly silicon. Each chip contains large numbers of tiny transistors that store data electronically. You can think of main memory as a bit reservoir. It is made up of a collection of storage locations, each with a unique identifier called an address. The CPU uses these addresses to read from and write to specific memory locations. In short, main memory acts as the workspace of the CPU, holding the instructions and data needed for immediate processing. In a computer, memory is organized in a hierarchy based on speed, size, and proximity to the CPU. The lower a storage type is in the hierarchy, the slower its bandwidth and the higher its access latency from the CPU. Registers are at the top of the hierarchy. They use a very small amount of extremely fast memory, providing immediate access where speed is crucial. Cache memory sits in the middle. It uses a moderate amount of medium speed memory to store frequently accessed data, improving overall performance. Main memory is lower in the hierarchy. It is large but slower, storing data that the CPU accesses less often. This hierarchy balances speed and cost, ensuring that the CPU can work efficiently while having access to both fast and large memory storage. The cache is a small, fast memory located between the CPU and main memory. Its purpose is to reduce the time and energy required to access data from main memory. The cache always holds a copy of a portion of main memory, usually data that was recently used or computed. When the CPU needs data, it first checks the cache. If the data is found, it's called a cache hit, and the CPU can read from or write to the cache much faster than from main memory. If the data is not found, it's a cache miss, and the CPU must access the slower main memory. The hit ratio or hit rate is the percentage of memory requests that result in cache hits. A high hit rate means the cache is effectively speeding up the system by keeping frequently used data close to the CPU. The CPU processes instructions in a program by following a series of steps known as the machine cycle. Each cycle consists of three main stages: fetch, decode, and execute. The fetch stage means that the control unit directs the system to copy the next instruction from memory into the instruction register in the CPU. In the decode stage, the control unit interprets the instruction, translating it into binary code that specifies the operation the system must perform. And in the execute stage, the control unit sends the instruction to the relevant CPU component, which carries out the operation. This cycle repeats for every instruction in the program, enabling the CPU to process data systematically and efficiently. Three important concepts in hardware architecture are pipelining, latency, and throughput. Pipelining is the technique where operations are broken into sequential stages, and the output of one stage becomes the input for the next. It allows multiple instructions to be processed simultaneously, improving overall CPU efficiency. Think of it like an assembly line in a factory. Latency refers to the time interval between a cause and its effect. In computers, latency is the total time required for data or an instruction to travel through the system from one location to another. Lower latency means faster response times. Throughput measures the rate at which tasks or data can be processed. High throughput indicates that the system can handle large volumes of data efficiently, making large-scale computations feasible. In essence, pipelining reduces effective latency per instruction and increases throughput, allowing computers to operate more efficiently.